We've talked before about permutations previously. And permutations are about ordered arrangements. So order is important with permutations, we've seen in the past. With combinations, however, order is not important. So a combination is a selection made regardless of order. So selection, it's not an arrangement, a selection. And the order is not important. Okay, so a couple of key words. And back when we did permutations, we're talking about arrangements and order for permutations. And for combinations, we're talking about not order, we're talking about a selection. Pardon my untidiness there. Selection, no order. Make sure we note that. With permutations, we previously saw calculations involving NPR. We're going to see that with NPR. With combinations, we're going to see calculations involving something called NCR, C for combinations, of course, which contrasts to the P for permutations. When we looked at NPR, we looked at n distinct objects taken R at a time, and we called that permutations with restrictions. Similarly, with NCR, we're looking at also n distinct objects taken R at a time. So it has some similarities and some links to our prior learning. A way to contrast these ideas in a simple manner would be to consider, let's say we're choosing objects, maybe, just indistinct objects that we reach in and grab at random, perhaps, and we're just looking at selecting objects with these letters W, X, Y and Z painted on the side. And how many different ways are there of choosing two letters from this set? W, X, Y and Z. So you could draw a simple tree diagram. This is not the way I want you to do it long term, but just beginning where this top row is the first choice. It could be a W, and if we've chosen a W on the first choice, we can choose an X or a Y or a Z on the second. I think you get the idea based on maybe all the work and probability you've done in the past. If we choose an X, W, Y, Z are our choices. W, X, Z if it's Y on the first, and I'm pretty confident you've got the idea of this W, X and Y if we get Z on the first, and we can list all of our outcomes. That would be WX on the first, and WY, WZ, and we could keep going and listing all of them. We'll have two letters in each output, each set, if we're making choices of two. If we've got WX here, and this one here, I'll just write that a bit more neatly just to make sure you can see it. That's a W, as you might remember. This XW would be listed here. I'll just put this one in. I won't write the rest in. XW. Those two are the same because with combinations, the order doesn't matter. So we haven't actually got as many selections that can be made with combinations as permutations in this sort of situation. And I've just completed that same idea down there quickly on the right. So these pairs that you see in each row going along are the same, okay, because order's not important. You just look at what you've got. You look at just what you've selected. So in this case, there's 6 different selections that can be made 2 at a time. And that's different to the number of permutations, because all of these outcomes at the end of this rough little tree diagram, and it is rough, they're all separate permutations, but they're not necessarily separate choices or selections based on combinations. So we've got 6 versus 12 in this case. 12 arrangements versus only 6 combinations. Okay, so to get this happening a little bit more quickly now, to suppose we want to count the number of ways that 3 students can be chosen from a group of 7. So using the letter thing, but we're expanding this idea out a little bit more. So how many ways can we choose 3 students from a total group of 7? So let's again use letters. Okay, well, BDE is one way of doing that. However, just with that combination of B, D and E, we've got all these different permutations. From our previous work, we know that we've got 3 factorial. Okay, and 3 factorial is 6. And you can see the 6 listed here. So in fact, each of these 3 factorial permutations are the same when we're talking about combinations. All right, so this is all one combination, yet it's 3 factorial permutations. So there are 3 factorial times as many permutations as combinations in the whole activity. So what we've got, that would create this little equation here. So 7p3 would be the same as 7c3, whatever that is, and we're learning about that now, times that 3 factorial. So we can rearrange that, and 7c3 would be 7p3 over 3 factorial, and basically we link back to other previous work, aka NPR is n factorial over n minus r factorial, and so we can go there via this and come up with that. So 7c3 would be that, which is that, and it's still divided by the 3 factorial. And this is how we establish our formula for NCR. Please note that NCR is the number of combinations of n objects taken r at a time, and it's given by the formula NCR is n factorial over r factorial times n minus r factorial. Important to note. So we shall finish with a couple of illustrative examples. Going to look at the first one here. A pizza can have 3 toppings chosen from 9 options. How many different pizzas can be made? And the first thing we need to do is identify that it's an NCR problem, because we're looking at the number of combinations. Alright, it's not a permutation problem. Okay, because what makes a pizza different to the other is the combination of the toppings. The order's got nothing to do with it in such a situation. I'm sure you'll agree. So there with 9C3, we enter that in. We can either expand and cancel, or we can just enter it straight in, and we get 84. So we can choose 84 different pizzas, or 84 different pizzas can be made. It's the same thing essentially. The next one, how many subsets of the set 1 through to 20 have exactly 2 elements? Now, this is very similar to what we saw earlier in the video. It's clearly an NCR. We've got 20C2. Alright, if you've forgotten what I mean, just go back to earlier in the video, about 5 minutes ago. So 20C2 is 20 factorial over 2 factorial times 20 take 2 factorial. And again, you can expand and cancel, or you can just enter it in your calculator if it allows you to. And we get 190 ways of choosing 2 subsets of 2 elements based on that set of 20 integers there, 190